This crash? Completely preventable, and the code behind it decides everything. Does your program survive in production, or does it page you at 3 in the morning? So, here is the deal. I spent the last few weeks going through the official Rust anti-patterns catalog, Clippy's 800 plus lints, the official style guide, the Rust patterns book, and the 2024 edition practices that just stabilized. And I found the 10 most costly mistakes that Rust developers make in 2026. We are talking about everything from crashes in production to zero copy performance traps. Let us fix them. I compiled this video from real sources, not just opinions. The official anti-patterns catalog, the style guide, Clippy's lints, the patterns book, and the 2024 edition practices. Every claim here is backed by a written reference linked in the description below. Now, whether you are shipping a small command line tool, a high throughput API handling thousands of requests per second, or an embedded system with limited memory, these patterns help you everywhere. They save hours of debugging, they cut memory usage in half, and they make your code actually readable by your teammates. Let us dive into the number one mistake. Number one on the list, the Unwrap epidemic. It is the single biggest cause of crashes in real Rust services today. And once you understand why, you will never look at Unwrap the same way again. Here is why this matters so much. A missing config file, badly formatted JSON, or a user that simply does not exist. These are recoverable errors. They are expected failures that your code should handle gracefully. But Unwrap turns every single one of them into a hard crash. And in production, that crash is a 3 AM phone call that wakes you up. Let me show you exactly what I mean. On the screen, you can see the wrong way. Unwrap on a file read, unwrap on a JSON parse, unwrap on a hash map lookup. 3 panic points for 3 recoverable errors. Now look at the right side. The same work handled properly using thiserror for library errors and anyhow with context for rich application error messages. And please, I am asking you directly, stop using Unwrap in production code. Use expect only for a genuine invariant. That's a condition which, if it breaks, means your logic itself is wrong. Then, a crash is the honest outcome, and the message tells you exactly what broke. Here's the full decision flow. If an operation can fail, return result and use the question mark operator. If a value might simply be missing, use option. If it's a genuine bug, use expect with a clear reason. Library errors use thiserror enums. Application errors use anyhow with context. The Rust FAQ puts it perfectly. Unwrap turns a recoverable error into a crash. In production, a missing file, a bad parse, or a network timeout becomes a crash instead of a handled error. That's the 3 AM story every time. This is the big one. The borrow checker is not your enemy, it's your architect. Every clone you add just to make it compile is technical debt, and it compounds with interest. Here's the wrong way. 3 clones, 3 times the memory. Here's the right way. Borrow for reading, then move the value when you're done. The compiler proves this is safe at compile time. Zero runtime cost. I benchmarked this on a real web service. Cloning request data at every step tripled memory usage and added 40% latency. Switching to references cut memory by 2/3. A smaller example shows the same idea. A function that takes a string forces an allocation every time it's called. Take a string slice instead, then it works with literals and owned strings and allocates nothing. Here's the ownership decision guide. Read only access, use a reference. Need to mutate? Use a mutable reference. Sharing read only data across threads? Use arc, the atomic thread safe reference counter. Shared mutable state across threads? Use a mutex or channels, not reference counted ref cells. And if you only need mutation occasionally, the cow type handles it, copy on write. And please, stop wrapping everything in a reference counted ref cell. That's not clever. It's a sign the ownership model is still fighting you. 2 more quick defaults. For string parameters, ask for a string slice or anything that can be borrowed as one. For collections, ask for a slice, not an own vector. Next, index-based loops are a habit from C and C++. In Rust, they're verbose, error-prone, and the optimizer doesn't love them either. The wrong way is a manual loop with a bounce check on every single access. The right way is an iterator chain, filter, map, sum. It's cleaner, it composes, and the compiler turns it into assembly that matches a handwritten loop and usually beats it. One honest caveat. Don't force iterators for complex multidimensional work. A 3x3 image blur, Write the nested loops. It's clearer and the optimizer handles it beautifully. Now, the collect trap. The bad version collects into two intermediate collections, two allocations. The good version does a single pass with zero intermediate allocations. Benchmarks prove it. On large datasets, one fused iterator chain is 10 to 100 times faster than multiple collect calls. The optimizer fuses the whole chain into a single loop. Unsafe is not a performance button. It's a contract you promise to uphold. The moment you write unsafe, the compiler stops checking for you. You are on your own. Here's the wrong way, using unsafe to bypass the borrow checker. If I equals j, you end up with two mutable references to the same memory. That's instant undefined behavior, no warning, no error, just silent corruption. Here's the right way, split at mut. It hands you two disjoint mutable slices and the compiler proves they never overlap. Zero unsafe, zero undefined behavior risk. When do you genuinely need unsafe? For talking to C libraries, for performance critical code, for implementing your own collection. In those cases, follow these 6 rules. Rule 1. Exhaust safe alternatives. First, split at mut. Unchecked access with bounce checks may be uninitialized. Rule 2. Isolate unsafe into the smallest possible block, one operation per block. Rule 3. Add a safety comment on every block, explaining why the invariants hold. Rule 4. One unsafe operation per block. Clippy enforces that. Rule 5. Wrap unsafe in a safe API, so callers never need to touch it. Rule 6. Never hide unsafe inside macros. Callers must see it explicitly and document it properly. The safety section explains alignment, non-null, initialization, and that no other mutable reference exists. Clippy checks all of this for you. These aren't suggestions, they're guardrails. Your API is a contract. Bad APIs push errors into runtime. Good APIs make invalid states impossible to represent. The classic example, a function that takes a log level as a string. Type debug with a typo and it compiles fine, crash at runtime. Give it an enum called log level instead and a typo becomes a compile error. Enums over strings, always. You get compile time validation instead of runtime panics. Autocomplete in your editor, refactoring safety, all at zero runtime cost. Next trap, Boolean parameters. What does passing true mean here? Name, enums or a builder pattern make the intent explicit. The call side documents itself. Same story with public fields. Expose your internals and you can never change the implementation without breaking every consumer. Private fields, public methods, that's encapsulation. Concrete example. If you expose a vector of connections, every consumer depends on it. Switch to a connection pool crate later and you break them all. Keep the surface small. Over-engineered generics, 6 straight bounds just to print something. Use imperative or concrete types. Complex generics belong inside libraries, not on public APIs. Returning own data when a borrow would do, a getter that clones on every call. The right way, return a string slice for data you already own. Return an owned string only when you're creating new data. This single pattern eliminates a massive allocation overhead in real services. And yes, I benchmarked every pattern in this video. The numbers will surprise you. Let's walk the performance anti-patterns. 3 RGB bytes in a vector. That's a heap allocation for 3 bytes. Use an array of 3 bytes. It lives on the stack. 0 allocation. A hash map for 3 to 5 items. You pay for hashing, allocation and collision handling. A match statement compiles to a jump table and it's 10 times faster. Box trait object in a hot loop. Virtual dispatch, no inlining. Generic imperative, static dispatch, everything inlined. And converting a string before validating it, you allocate first, then waste it on an early return. Work with the string slice, allocate at the end. For deserializing from a slice, the hot path pays the full deserialization tax. 0 copy formats, skip the copy entirely. And collecting between chain steps means multiple heap allocations. One chain, 0 intermediate allocations. The difference again, clearly, a box trait object means heap allocation plus virtual dispatch. Generics are inlined, 0 cost. Imperative, 0 cost. Static dispatch via generics is 5 to 10 times faster than dynamic dispatch for simple operations. The optimizer inlines everything. Dynamic dispatch forces a lookup table on every single call. premature string allocation. The bad version allocates a string for every line. Even when most lines get filtered out, 90% waste. The good version checks first and allocates only when needed. Real numbers from a log processor, 10 million strings per second, 90% of them filtered. Using a string slice until actually needed cut allocations by 90% and tripled throughput. Small data structures. 3 RGB bytes belong on the stack. In an array, a vector adds a heap allocation, pointer in direction, and capacity tracking. And for 3 to 5 item lookups, a match compiles to a jump table. A hash map pays for hashing, allocation, and collision handling. Match wins 10 to 1. Style isn't a preference, it's cognitive load reduction. RustFMT ends the debate before it starts. The official standard 4 spaces, 100 characters per line, paling commas on multi-line lists, block indentation, no trailing whitespace. And for comments, use the double slash style, triple slash is reserved for documentation. Variable shadowing is encouraged in Rust. It's not a bug, it's a feature of more semantics. Instead of Hungarian style suffixes from other languages, use shadowing. Each shadowing moves the previous value, no mutable state, no suffix noise. The type system tracks everything, naming, types and traits in upper camel case, functions and variables in snake case, constants in screaming snake case. No Hungarian notation. Rust has real namespaces and real types. Just name things clearly. Project structure. Module first, create last. Keep the main file thin and let the library file re-export your public API. Split into crates only when you really need to. Procedural macros, strict API boundaries, or large independent sections that compile in parallel. Every crate boundary adds compilation cost. Don't split for the sake of splitting. Feature flags, optional dependencies with clear names, an empty default, and composable features. Now, Async. The 2024 edition stabilized async closures and precise capturing. If you're still writing async like it's 2021, you're leaving performance and ease of use on the table. The classic mistake, blocking in async. A plain file read blocks the Tokyo worker thread. Spawn blocking offloads that work to a dedicated blocking pool. Never block the async runtime. File EO, heavy CPU, legacy synchronous libraries, all of it goes to spawn blocking. Tokyo's blocking pool was built for exactly this. Cancellation safety. The select macro drops losing branches immediately. If the timeout fires first, partial data written mid-operation is dropped and that corrupts state. The fix. Wrap the non-cancellation safe work in a spawn task and abort the handle when the timeout fires. The 2026 best practices. Async closures from the 2024 edition, precise capturing with import rate, and Tokyo for the vast majority of use cases. In async apps anyhow with context for errors and always spawn blocking for blocking work. And if you're not running nextest in 2026, you're wasting CI minutes. It's 3 times faster than cargo test and it isolates every test in its own process. One Horizon's 2026 guide nails it, simply writing, Rust is no longer the flex it used to be. Async closures, precise capturing, cancellation safety, these are now table stakes. Testing. Next. Unit test with handcrafted data test, 1 case. Property-based test thousands. Snapshot test catch regressions in complex output. Property-based testing with proptest generates hundreds of random inputs, edge cases you'd never think of, not a number, empty strings, max integers. And when it finds a failure, it shrinks it down to the minimal reproducing case. That's the magic. Snapshot testing with insta. The first run creates a snapshot file. Every later run diffs against it. Output changed. Insta shows a visual diff, accept it or fix it. Perfect for APIs, CLI output and serialization. The 2026 Rust testing stack. Cargo nextest run 3 times faster than cargo test with per test isolation that catches leaks and beautiful output. Clippy with warnings treated as errors in CI. Cargo FMT with check. Cargo audit for dependency vulnerabilities. Bookmark this. This is your daily driver cheat sheet. Here's the decision matrix you will actually use. If an operation can fail, return result and use the question mark operator. If a value might be absent, use option. For string parameters, Take a string slice or anything you can borrow as one. For collection parameters, use a slice rather than an own vector. And when you need to return new own data, reach for string. Fixed size data, use an array on the stack. For small key lookups, a match beats a hash map every time. For multiple types known at compile time, generics with inbuilt rate give you zero cost static dispatch. Need runtime polymorphism? Try an enum first. It's simpler with no heap allocation. A box trait object is your fallback when the set of types is truly open. For shared mutable state, reach for a mutex or channels. And for code style, rust fmt always. Library errors. This error lets callers match on specific variants. Application errors. Anyhow with context gives rich messages with almost no boilerplate. Blocking work in async, spawn blocking. Testing, proptest, insta and nextest. And if you're fighting the borrow checker, restructure your ownership instead. Unsafe for performance. Profile first, isolate it into the smallest block and document every safety invariant. Then set up your toolchain once, rust up component, add Clippy and rust fmt. Then cargo install nextest, audit, expand, semver checks and outdated. Your CI pipeline, format check, Clippy with warnings denied, nextest run, audit, semver checks. Your IDE, Rust Analyzer for language support, inline type hints, autocomplete, refactoring, Tableau for normal formatting, typos for spell checking, and Cargo Watch to auto-run Clippy and test on every change. This tooling isn't optional for professional Rust in 2026. It's the baseline. Clippy with denied warnings catches anti-patterns before they ever merge. The underscore patterns. These are legitimate tools, not automatically bad practice. The misuse is the real problem, silently swallowing errors and forgetting variables. First, the discard pattern, a bare underscore with an equal sign. It drops the value immediately, like a coin in a fountain. Best use, explicitly ignoring a non-critical result. Danger, silently swallowing important errors or dropping logs too early. Clippy flags all of these. Second, the named underscore pattern, underscore followed by a name. It's a real variable that lives until the end of scope, but it doesn't trigger the unused warning. Best use, keeping a mutex card alive without using it. The name stays visible, better for future you and for AI tools. Third, the underscore parameter. A parameter required by the signature but unused in this implementation, standard and recommended. It clearly says, I know this is here and I don't need it. Practical rules against silent failures. Ignoring a result in production, log it or handle it. Need the value later? Keep the name. Plan to use it soon? Don't prefix it with an underscore yet. When a lint is justified, prefer expect over allow. Expect takes the lint name and a reason, and the compiler keeps checking everything else. Allow just hides the lint forever. Set it in cargo.toml. All Clippy lints to deny, pedantic to warn, cargo lints to warn. Then allow only the few pedantic lints that are too strict for your code, like module name repetitions. Final quick checklist. Can this fail in normal operation? Return. Result with the question mark operator. Only need a view? Borrow. Is it a programming error? Expect with a clear reason. About to write unsafe or a heavy clone? Pause and redesign. Does Clippy complain? Fix it. We covered a lot. Error handling with result, thiserror, and anyhow. Ownership, borrow by default, move when done. Iterators over manual loops. And the underscore patterns, discard deliberately with intent. Unsafe only when necessary, documented, and minimal. API design with enums, builders, encapsulation. Performance, static dispatch, stack allocation, zero copy. Clippy configured to deny. Style with rustempty and shadowing. Module first project structure. Async in the 2024 edition, spawn blocking, cancellation safety, nextest. And the decision matrix to keep it all straight. Key code from the Rust patterns book. The borrow checker is not your enemy. When code feels like a battle against the type system, you're usually approaching the problem incorrectly. That code changed how I write Rust. Stop fighting the compiler. Understand what it's preventing. The patterns that feel natural in Rust, ownership, borrowing, iterators, enums, exist for a reason. They align with the language's guarantees. If this video saved you one production crash or 1 hour of debugging, smash that like button and subscribe for more deep dives. Links are in the description. the complete written reference, all benchmark code, the Clippy config I use, and my cargo config for optimal defaults. And drop a comment. Which anti-pattern bit you hardest? Unwrap in production? Ref cells everywhere? Premature string allocation? Let's compare scars. Stay tuned and subscribe to the channel so you don't miss future videos. Thanks for watching. Write safe code, write fast code, write idiomatic code. See you in the next one.